Does that make sense? Style layers is a list of indices.
Right.
You don't get the length of the array and then find the range of it. Because that just gives you 0, 1, 2, 3, 4. The style layers could be like 2, 4, 8, and 9.
I'm using the I and mine is style layers.
Okay, let's get going. Sorry to be a bit late. Any questions as we? Okay, I see. Any questions as we get started here? Any questions? Okay. So I made a slight adjustment to the syllabus, and we're just going to. Let me see. I'm still casting. We're just going to, what I had was like transformers were supposed to be this week, and then like neural machine translation next week. But we kind of got a little bit behind, and we were just doing RNNs last time. So we're gonna do like a good chunk of the neural machine translation today, and then spend all of next week on transformers, and then like applications in machine translation and other things that transformers are doing. So just a slight change there. So you have to wait till next week for introduction to transformers, but it's not too far away. I think this makes a lot more sense just kind of structure-wise. So that's what we're going to do today. We're talking about neural machine translation with RNNs. So we've already talked a bunch about this. We've looked at these examples, but we're just going to get more into the details, and then in particular, like how these things are evaluated, and then like what advanced neural machine translation looks like, at least up to a few years ago. And like the ideas are still pertinent, it's just not being used with RNNs. So remember our whole the thing we looked at last couple of lectures, recurrent neural networks. You have this. You basically have your network is set up in such a way that it can take sequences as input and output sequences as well. And the very basic plain vanilla look to this is you have a hidden state, you have some input, you have some ways of transforming that into the same size, applying a nonlinearity entry-wise. That gives you the next hidden state that then is using this kind of recursive formula. In neural machine translation, we're interested in turning one sequence into another. This is the part we talked about. Turning one sequence into another, and we're going to look. We're going to have this kind of example here a bunch throughout today. Translating English into French, particularly, you're going to see I am a student, je suis étudiant many times. Anybody speak French? All right. Well, we might rely on you at some point, but actually, only just for correct pronunciation. You're just going to see the same phrases over and over again. But the idea here, remember, is that what we're trying to do is set something up so that we encode the entire English phrase in this case. And then we give that as input to, or as the initial hidden state to another RNN, essentially, and it's all one model, but another RNN that is going to then produce a sequence in the other language, in this case French. And we've seen this, right? We've talked a little bit about how this works. Throughout this lecture, we're going to have these tokens here, these underscores. They're going to represent our like boundary tokens. This like here's the start, here's the end. The RNN that is going to take our English phrase and turn it into a vector, we're going to call our encoder. And yeah, there's our boundary marker. We'll be producing these things, and then this red side here is what we'll call our decoder. And the decoder's job is to take that input, that hidden input coming from as many layers as we have, Here we're showing 2 hidden layers. You can have many. In the papers that we'll cite, there are 4 layers typically, but each one of those would have its own hidden state of each layer, and that would be passed as the initial hidden state into the decoder. That's how we're going to hook up this encoder and decoder. And when we get to transformers, you're going to see something very similar. We won't have RNNs, but there's going to be this notion of like encoding the sequence and then decoding it, and there's going to be kind of similar kind of connections of the hidden state or like the latent state of the encoder being used to condition the decoder. Okay, so a couple things we haven't really talked a whole lot about. I'm not going to talk in tons of detail today. I want to cover a lot of things, but we have these tokens. Typically this is going to be our words and our vocabulary for each language, and we need some way of turning those into vectors to be the input, so it can be used as input in the RNN, right? We need to be able to multiply a matrix times some vector representation of these words. And we saw an example where you might use like a one-hot encoding, but for large vocabularies that really makes no sense because you're going to have a lot of wasted dimensions, a lot of wasted computation because there's of all those zeros. And there's a lot of ways to do this. There are a number of what look like more or less like unsupervised methods for basically turning these something like a one-hot into like a dense representation in a much smaller embedding space. And these go by the names of things like word-to-vec. You might have heard this before. Word-to-vec, glove. There are a variety of algorithms like this, and they're usually taken as a starting point. Basically any kind of reasonable representation, can work here. You can also imagine learning the embeddings as part of like an end-to-end process. But typically you would just, you'd use any kind of reasonable embeddings, and then the network would learn to work with those. Right, we have initial states, initial hidden states for each of the layers. As I said before, they're typically set to 0. At least that would be the case for the encoder. That's not going to be the case for the decoder because, of course, the output of each hidden layer of the encoder is going to be the initial state for the decoder. And that's how this is really important, that's how we're conditioning the decoder on the encoder, on the output of the encoder. Somehow these vectors that, represented by these lines here, that vector there is some kind of, aggregate representation of this sentence, "I am a student." And having seen lots and lots of examples like this, it's going to just the decoding RNN is going to know how to take that initial state and output the correct French phrase in this case. There can be many layers here. I'm showing 2 just to show that there's more than one, but there could be many. Like I mentioned before, there's often in these early models from 2014-15, there were 4 layers. You can have more. This is one of those things that's like a hyperparameter that you would tune for your problem. And the forward pass follows all of these arrows. By the way, I guess we haven't really talked a whole lot about this, but in this, as we add layers to recurrent neural networks, we talked about there are 2 things that go into computing the next hidden state in any one of these cells, right? It's this input and the previous hidden state. But when you're here in a next layer beyond the first one for an RNN, the input is no longer just some representation of the actual token, but it's actually output of this hidden state, right? So like as we go deeper and deeper, that the context that we've computed up to this point becomes the input to the next layer, and then the next layer, and so forth. And so that's how you get this depth. And this is true throughout the entire, both in the encoder and the decoder. Yeah, follow the arrows for the forward pass. We talked about this. Remember, vanilla RNNs just have this very simple kind of computation graph. I mean, there's some black box stuff hidden here. But remember when we looked at things like LSTMs and GRUs, and these actually had two states that were tracked. One is like the typical hidden state. This other was like the self state. And we solved a kind of gradient problem, exploding by clipping gradients, but the vanishing one by having something similar to what we saw with ResNets, a branch in the computation graph that did not have like iterative multiplication of matrices involved in it, which is what would give you either the exploding or vanishing problem. So you very rarely see plain vanilla RNNs. You will more often see LSTMs. All right. And then again, just more along the lines of review here. The way that we compute losses here is this is all input, right? The network has got a bunch of parameters. It's outputting these vectors. From one hidden state to the next, and then our final output is going to be it's a classification problem over the vocabulary. So what that means is we're at each one of those at each cell here in the decoder, whatever the correct token is, we're doing a classification problem. And as we saw, if we're using cross entropy, what this looks like is actually a negative log likelihood loss, right? Like it reduces down to that, so you have this negative of a log of the probability of the correct token, and we're trying to minimize that. How do we minimize log or negative log? We make the probability what value? You want to minimize the negative log, then the probability. So the minimum of the negative log on the interval from 0 to 1 is which value? What's the minimizer there? Picture log. Go log looking like this, right? From like 0 to minus infinity, and it's going up through what value at 1? 0, right? So if we take the negative, now we started at infinity and work our way down to 0. So the minimizer is when the probability is 1. And that's exactly what we're trying to do. We're trying to maximize the probability, make it as close to 1 as possible for the correct token. And because this is a cross entropy, that's a distribution. The probability on the token is 1, and the probability on all the other tokens is 0, right? And as we get closer to 1, that's more like it. So that's we just reminding you about classification and cross entropy there. So there's going to be one so for this sample, remember this is we had it like for each image when we were doing classification on images, like ImageNet classification. Each image was an input, and you had your class, whatever the object was in that image. Here, your sample is this like pair of phrases, and then you actually have multiple labels here. Well, it's the whole sequence here, the whole sequence you want to decode to. But for each token in the phrase you want to decode to, so like the phrase you want to translate to, you're going to have a contribution to the loss. That's going to look like this negative log likelihood term here. So we're going to have one for je, because we want the output from here to produce je. we want the output from the second one to produce sui. And this is where we get the pronunciation. Those who raise their hands about perhaps you can correct that or whatever. Étudiant. And then, of course, we want this thing, as we said before, because phrases are variable length, we want to be able to know when we should stop. And so we emit a token here, like an end of phrase token that we're just kind of indicating by underscore, as a way of saying, okay, this is where we stop. And using those losses, we are now going to, backpropagate. And you just follow all the arrows. And you just get a lot of, you get a lot of terms that are contributing to the partial derivative for each parameter at each part in this network. And remember that the parameters are shared. There's actually different parameters for the encoder and the decoder, but within those ones, the parameters are shared. And so there's an accumulation of gradients along all the pathways into any one cell here and then the parameters as represented by that cell. So it's a little bit more complicated than we saw in the classification case, but conceptually it's pretty easy. We just add all those gradients together, and that's your full signal that you're going to update your weights with. Okay, questions so far? It's really just review of what we've seen. Yeah.
Yeah, regarding the question regarding the loss. So at the end, do we add loss for each word to complete the total loss, just like how we?
Yeah, exactly. Like you would you have a total loss. You'd add all those loss terms together. Yeah, and you want to minimize. You're trying to minimize that. Good. Yeah, we talked about this before. So. When we're training, we have these pairs of phrases. We have the English phrase and the French phrase in this case. We want to translate from English to French, and so we know how to supervise the training. We just describe how to do that. And at test time, of course, we don't have the correct phrase, or the point is to produce it. And we talked about how to do this as well, right? Is that this is going to produce a probability distribution because we're doing cross entropy. We have this soft max we apply to scores. We get the probability distribution over all the possible tokens. Obviously, the vocabulary is going to be larger than what we're showing here, but for purposes of illustration. And so, what we do at test time, we take the most likely word, the word with the highest probability here, and this one has an additional word in here, moi. Our French speakers, what does it mean? Me. So what's that? Yeah, it means me. So this thing isn't quite trained properly yet. We really wanted to produce je, but it produced moi. So the highest probability was assigned to moi. And at test time, we don't know what we're supposed to get, right? So we just take the most likely, and then that becomes input for the next stage of the decoder. That's going to produce for us another distribution over the vocabulary. We'll now take the most likely token there, in this case sui, so it's a little bit more, but that's correct. That's what we'd like to see. And then we do it again. You get that the most likely term or token next is étudiant, and then we get that the next after that is this underscore saying we're done. This kind of algorithm is known as beam search. These are beam search decoders. None of that matters too much. It's just that you have a fixed length set of tokens that you're taking the most, like in a semi-greedy way, producing this sequence over. And so this is almost right. I mean, this is just kind of an illustration's sake, but this is almost right. this should have been je, like this isn't grammatically correct, right? Me, am, student. But, you know, it's pretty close. You can imagine how, like, as it's learning the train, like maybe it gets to this point and it does this, but as it maybe, you know, as you train further, maybe it learns to, you know, to assign the je the highest probability. But, you know, this is the idea. And then you'd want to evaluate that, right? You say, okay, well, I got a translation here. Is this a good translation? And we'll talk about that in a second, about like how in these bilingual translation problems, these are evaluated. But we're going to say that for just a second. I'm not quite there yet. But yeah, this is the idea. So at test time, this is how you produce a phrase. And again, you produce until you get the end token. Okay, so all of this kind of came out these ideas were kind of, you know, published and used for the first time in 2014. You have two papers that are basically doing like the same thing. They're using these RNNs, these encoders and decoders, to do this translation. The first paper here, first author is Ilya Sutskever. You remember we've already talked about him. Where have we seen his name before? History lesson. 2012, AlexNet. Who were the three authors in that paper? Somebody named Alex. Somebody named Ilya Sutskever, and another person named Jeff Hinton. So Ilya has a paper, has like the most important convolutional neural network paper of all time, probably, and then has one of the most important papers applying neural networks to language of all time. Here, it's no doubt, or there's no wonder why he's now the chief scientist at OpenAI. But anyways, just a bit of history there. Somebody mentioned Bengio. Bengio is the senior author on this paper right here. Joshua Bengio. Yeah. So, a lot of, you know, like the more famous groups in these areas kind of became famous maybe by these papers. But anyways, these ideas came out. In the end, like the kinds of networks that we're looking at are known as seek-to-seek, sequence-to-sequence, like literally SEQ to SEQ. You see that a lot. And this is like the first time that neural networks were used to, in an end-to-end way, train the neural machine translation system. There have been a lot of like statistical machine translation systems up to this point, where, you know, they're in their own ways trying to represent statistics of the different languages and how to match them up. This is like literally, you know, give me pairs of phrases that should translate to each other and just, you know, learn to associate them through these encoder-decoder RNNs or seek-to-seek, and you got great results. Although we'll see not quite state-of-the-art yet on these papers. Was there a question? Yeah.
Yeah. Can you just go to the previous slide? Previous slide.
Sure.
So here we are passing the word that was generated into the next time step, right?
Yep.
So wouldn't this cause an error propagation at this stage? And
Wouldn't this cause what?
An error propagation, because if the first word is predicted wrong, the error, you know.
Well, this is at test times. We're not backpropagating anything.
I'm talking about the error. Let's say we predicted the.
Oh, I see. Error propagation. Yeah. Yeah, it can. Right. You're absolutely right. Like if you start at the beginning of the phrase is wrong, then yeah, it's more likely the rest of the phrase is wrong, right?
Yeah. So in that case, would it be ideal to train the teacher also the same way rather than teacher forcing it? Because in case of teacher training, you are trying to teacher force it by feeding it the right output. And in that case, error propagation doesn't happen during training. But here, error propagation happens. So wouldn't it be better that the network learns to, you know, overcome the error propagation during training time itself by not feeding the ground truth outputs during training?
At training time, this is always the correct. You're always going to put the correct one.
Instead of putting the correct one, can we not keep the word which was generated by the network itself?
I just don't understand what you're asking. I'm sorry. Try again.
Yeah, maybe we'll try offline after the class.
Okay, sorry. Yeah, there's probably a great idea there, but yeah, in general, because of the sequential nature here, you're going to have this idea of error propagation. I mean, you could produce this. You could produce this sequence in a different way. In fact, the seek-to-seek paper, I think, had better results if it reversed. I mean, it's not quite what you're saying, but if it reversed this phrase right here. So if the first word was student, if this reversed and it input the sequence as student AMI, it got better better evaluation results in when translating. If it did that, the reason they said that is because it brought instead of having the first token here be fairly far away from the first token here, it actually brought them together so that it was easier to learn some of that early to get the beginnings of the sentence or the beginnings of the translation correct. But that's one more detail. But yeah, maybe that's related to what you're saying, maybe not. But basically, what all these were, I mean, in 2014, this is absolutely revolutionary. Now it kind of seems like, oh, I just learned that in the class, no big deal. I know what an LSTM is or whatever. But these deep LSTMs, like 4 layers for both the encoder and the decoder, and that's true for the seek-to-seek paper. This other one, Chodo, this is the Bengio paper. They had these GRUs, so not LSTMs but GRUs. GRUs are slightly more performant than LSTMs, but not too huge a difference. There were other attempts using CNNs, but whatever. So they did all this, and how are they evaluated? So somehow the community this is definitely true before the neural networks were on the scene, but the community that was trying to work on machine translation, had come up with ways of evaluating this, and this right here is a very common framework for evaluating these kinds of translation systems. It's called BLEU, although it's spelled BLEU. It stands for Bilingual Evaluation and Understudy, and it's this formula right here. And so this formula's got a bunch of different terms in it. So let me just kind of go through and tell you a bit about what's each of the terms here. So let me start with the PN. This is the most important part. This is something called modified precision, and this is a little bit complicated. So how do you tell if a translation is good or not? Well, you want to do something like you have your phrase in your source language, and then you want to translate to your target language. And like we mentioned before, there's often many valid ways you could translate that sentence and have it be valid, right? And have it make sense and have the right meaning. So there are often a handful of reference target translations. And so you want to be able to kind of take that into account, that this thing, will translate, we'll create a sentence and it might be like any one of the many reference translations. And you also want to be able to kind of take into account the fact that maybe it got most of the translation correct, but not all of it. You want to be able to score kind of getting it partially correct, so to speak. So the way that this is done is to focus on n-grams. So n-grams are just literally subsequences of tokens in your phrase. So n tells you how many of those tokens you're taking in a row. So 1 gram or unigram would mean just a single token. 5 gram or 2 gram would be 2 tokens. Obviously, keep going 3 grams, 3 tokens, 4 grams, and so forth. And so really what we're talking about here is like, in the, je suis éditant, there's 3 tokens there. So there's 2 bigram, there's 2 bigram sequences in there. Je suis and suis éditant. There's 1 3 gram, there's no 4 grams, so it's not that long, and so forth. So what you do is you kind of decide, all right, what I want is to pick like the length of n-gram, and then I want to go through, and I want to basically, like, for all of my candidate translations, I want to just count how many times a particular n-gram within that candidate translation occurs. So that's in the like human translated, like the correct or target translations. That's in the denominator here. And now in the numerator, I want to have the same thing, but for the reference translations, or sorry, for the machine translation. So like what my model actually translated. And I actually can, because there's a somewhat stochastic nature here, I can actually produce a number of translations. If I don't take the most likely one, but if I sample from that, I can get multiple translations. So what I want to do is I want to look at all those translations that I created from my algorithm, and I want to look at all the possible n-grams there, and I want to just count them up. If they also occurred as one of the n-grams in the human translations. So you're getting a fraction basically of like all the possible n-grams in the translations. How many of those did I actually get right? There's a slight modification here in this clip, as you see here, and this clip is really just a way of making sure we don't do any overcounting. It's like there's an expected max. You calculate a max number, like a possible n-grams, and you don't let this number here get above that. So, anyways, what that does is that makes this number between 0 and 1. So for every pair of translations, or for every translation, so pair of phrases here, or pairs of phrases, I should say, all the possible translated phrases done by humans, I can produce my human or my machine translations, and I can do this kind of comparing here. And I get a number between 0 and 1. It's known as precision or modified precision because of the clipping. So I do this for all of my 1 grams, 2 grams, 3 grams, however many grams I choose. And you can see it says, we say in here somewhere, yeah, default is usually 4. We usually look at this up through 4 grams. Okay, so then we take the log of that. We're going to then take the exponential of that. So there's a kind of weighting going on here, but like in the log space, rather than say just like in an arithmetic space. So I'm weighting that. This is 1 over whatever this n is right here. That's the typical way to do this. I exponentiate that. So now I've got this is looking something like perplexity if you've worked in this space before. But anyway, some measure of like how well I'm doing here. And then, so larger is better here. And and I just have an additional penalty here that obviously, if my translations, I can make like really long translations. You can imagine I have a system that makes really like for every time it translates, it can translate like repeat itself over and over again, and put like various n-grams together. That would obviously be a horrible translation. Up to this point, this way of scoring wouldn't have caught that. So you have this penalty here, which is there's a kind of expected length for the translation, which is represented by R here. And if by C. And if the actual length here goes beyond that, then I start to reduce whatever this score is here by this exponential factor, right? So if the translations are quite large, this is going to be quite small and really reduce my score. So it's a way of penalizing translations that just like produce all the engrams, for instance. Like that would, again, like that would be, and this score would get the highest score. We'd have ones for all these, they'd all be great, but that's not what we want. So, there's that penalization term, and so this is known as the BLEU score, and this is what so many of these these neural machine translation systems and other just machine translation systems are stored with. Okay, so knowing a bit about that, we can look at this and say, okay, so up to 2014, SMT stands for statistical machine translation. So this is machine translation, but not with neural networks. This is like state of the art using, statistical models of language, however that was done. And state of the art for this English to French task got a BLEU score of 37. And on average, these sorts of systems, would get something like a 33.3. So the seek-to-seek machine translation system gets a 34.8, which is not 37. So it's actually not state of the art. So when this comes out in 2014, it has a score that's better than the average statistical machine translation system, but it's not state of the art. Interestingly, people combine the seek-to-seek model with some of these other statistical machine translation systems, and they got 36.5, which is still not state of the art. But as this slide tries to point out, with relatively fewer, less time spent in like producing these kinds of systems than the research that gone into these SMTs, we were getting pretty decent BLEU scores. The good news is that this is the end. We actually get state-of-the-art models here pretty quickly, but this is not like 2012 ImageNet competition where convolutional network blows it out of blows the original or the other non-neural network competition that we like. But doing pretty well. And it's at this point that we should probably think about what can go wrong in machine translation. So here's a bunch of examples of things that can go wrong. So if you literally just let a machine translate, you get all kinds of things that there's maybe some resemblance to the way that to what was actually being expressed in the original language, but when it comes out, it has a meaning that is definitely not what was meant. Right? So I don't know what this is right here. This probably was something like, it's like we're not selling you live chickens, we're selling you like chickens to eat or something like that, right? But somehow the translation says your sale of chicken worth, right? Not right. Deep fried baby, certainly. I actually have no idea. If anybody recognizes any language here, can give us some insight. That'd be fun. But yeah, I'm sure it's not deep fried baby. It's probably something like this is a kid's menu, so maybe it's like a kid's something or other, but it came out deep fried baby. This one you can kind of understand. Go backward towards your behind. I mean, it's something like you just want to go backwards, but it somehow came out that way. Yeah, this is. Who knows what's going on here? Meat, muscle, stupid bean sprouts. I have no idea why the stupid got in there. This can get really bad. This public figures can have, this is actually from not too long ago. This is translated by Microsoft's best translation systems, and this famous Israeli singer gets praise from the Prime Minister, and he says, "You're a real cow." And I have no idea why I would say cow. I think it's something like it's supposed to be a term of endearment, but of course it comes out really horrible in English. Other ways this can go wrong, they got the numbers wrong. So instead of getting like 1,500 eggs, they got 15,000 eggs in an order. I mean, lots of things can go wrong. Cream milk with coconut humans is the best one right here. I can't find it on Google, but it's delicious. I saw this once on Twitter. I thought this was funny. Foreign candy always seems like the output of a slightly undertrained neural network. Dairy milk, musk sticks, pineapple lumps, frogs alive. It's actually not a translation problem here. It's just the comment that like poorly trained neural networks or like not state-of-the-art neural networks might produce translations that oftentimes leave you kind of wondering, like, does a pineapple lump sound, appetizing? I don't know. Okay, so what are some of the limitations here? Well, there's at least 3 that we're going to address real quick in terms of how to turn these things into state-of-the-art translation systems. Pre-transformers. So one is dealing with vocabulary size, right? Vocabulary sizes can be huge. We have to do this classification problem at each step of the decoding of the phrase, right? And so how do we deal with vocabulary size? Is there something that we can do differently than just like straightforward classification and deal with it? Sentence length. So the longer the sentences get, the harder these encoder-decoder RNNs have, or the harder time they have because of just the need to kind of aggregate so much information across such large sentences, such long sentences. And then there's take any 2 pairs of languages, like they're not like equivalent, right? Like language is complex. Each language has its own complexities. Those could be, there's a variety of kinds of complexities, and we need some way of dealing with the differences between languages and their complexity, right? I think we should expect it to be easier to translate between 2 romantic languages, say Spanish and French or Portuguese or something like that, than to say go from Spanish to Finnish or something like that, right? The Finnish is already very complicated and they have very different grammars and things like that. So how do we deal with those kinds of things? So what we're going to do here in the last little bit is just kind of see what was done to deal with these problems. As we get started, we'll just kind of say what each one of these, what the basic solution is here, and we'll talk about each one. So the solution to the first is what's known as the copy mechanism. We'll talk about that first. The sentence length is interesting. This is where we get the notion of attention introduced, which then becomes the important idea for transformers. And then this language complexity. One of the complexities there is just very complex languages, very complex grammars, things like that. So we then default to a character level translation instead of at the word level as the tokens. This is more advanced neural machine translation. So again, remember at the core of this is a seek-to-seek, encoder-decoder RNN. But these will be additional algorithmic components put on top. All right. So when it comes to vocabulary, I already said this. It's we're trying to do this classification problem over what could be a very, very, very large vocabulary. When we were doing ImageNet, there was just 1,000 categories, but languages can have hundreds of thousands of tokens, and that's orders of magnitude larger than 1,000. So that's probably a problem. How do we deal with that? So the way that this is dealt with is to still maintain that this is still going to be a classification problem, but what we're going to do is we're going to look at our corpus representing all of the examples of a particular language, and we're basically going to like pull out the words that are most frequent. Maybe not the most frequent words because maybe we see those too often, but we're gonna pick out a much smaller set that we expect to see a lot and that we want to be able to translate. So we kind of do a little bit of analysis on our vocabulary, and maybe we get ourselves down to something like 50,000 tokens rather than hundreds of thousands or even a million or something like that. 50,000 is still quite a bit larger than 1,000, but this was found to be a decent size. Oftentimes it's 50,000, 20,000, something like that. We're still going to do classification over this vocabulary of 50,000. But what that does mean is that there's a whole bunch of tokens that we're going to see that don't exist in our vocabulary. We don't know, like they're not there. So we don't know what they are. So we're going to have to deal with them in some way. So the way that we begin to deal with that is to add one more token in here that's like our unknown token. So anytime there is a word here that that doesn't exist in our vocabulary, we're going to replace it with this token that does exist in our vocabulary, and it's just the unknown token. Okay. And what we don't forget is that this is still a pair of phrases, one in English and one in French. And when we come down here and we've done this replacement, we still have the same thing. And what's typically the case is that there will be some relationship between the unknowns, the unknown tokens, in both languages, right? If it's rare in one language, it's probably going to be rare in the other language. Names are a particularly obvious one. We're not going to have those as tokens. Or place names, things like that. Okay. So if that's, if that can't be the only solution, obviously, that actually doesn't help us. We seem to be losing information. But what we do is that on top, so we learn to do all this translation. We learn to do, oh look, there's Ilya again. Of course, what happened here is that Ilya and Jeff Hinton and a couple others started a company called DNN Research that was sold to Google. That's how Jeff Hinton joined Google Brain and Ilya at the time. And now all these people were working at Google together. So 2014, 15, those years, all these well-known names were working together. Copley is really well-known in the language community. Anyways, they're all working together on these problems, and they start to, they're solving these problems together. So what do they do? What's this copy mechanism for the unknown? Well, you do the translation as usual, but what you do at the end, after you've done the translations, you're ignoring the unknowns essentially. You do this post-processing on the translations that's looking at the unknowns. And how does this work? Well, it's basically you're going to have this additional component that works after you've done the neural machine translation that will learn something about alignments. So, for instance, it'll learn something like, what place names look like, and that those those relate to each other kind of one-to-one. They learn things like in English, like an adjective comes first, but in French an adjective comes after, and so you look at those things you notice those things in the original sentence, and then you just apply those relationships to the translated sentence. And it's so far maybe this doesn't seem to be solving the problem. But then you just do the obvious thing, right? And that is you look at the thing that needs to be filled in. You know what it is in the source sentence. You just look it up in the dictionary, the translation in an existing dictionary, and you put it there like where it should go. So we know that, so in the original, the original English sentence, it said ecotax. We just look up how, like, what is the French word for that, and we just put it there. Place names we just copy straight across, and that's it. And if you do that, actually, you all of a sudden have a state-of-the-art system for English to French translation, for example. So just by doing the seat-to-seat, but doing this annotating these rare words, and then doing this kind of simple replacement with dictionary lookup, you now go from the state-of-the-art BLEU score at the time, 37, to 37.5. So now this is state-of-the-art. Not a huge jump over 37. I mean, actually, we don't really understand what 0.5 means in terms of like being better, but it's better according to the accepted way of evaluating these things. So yeah, that's it. But just doing that, we all of a sudden go, we have a state-of-the-art system. That may feel like let down if the solution wasn't any harder than that. Yeah, you feeling like that? Or do you have a question?
Yeah,
Yes.
regarding the Durrani et al.'s graph that I see there, why is there a drop at 1500 and there is another rise? Because more rare plots should obviously be difficult to calculate. I see upward curve in case of blue curve. After the 1500 mark.
Why is it? Are you asking why this one's going up here?
Yes.
I don't know. Not sure. That's a statistical machine translation system that I don't know anything about.
So is higher better?
Higher's better. Yeah, higher's better.
Where would human be?
That's a good question. I don't have those. Those numbers aren't here. I don't know. I mean, in some sense, human should be. If you think about how the BLEU score works, how I described it, the denominator is human translations. So it's actually, yeah, I guess I do know. It's a 100. Yeah, I do know the answer to that. After I think about it for a second, it's 100.
So these aren't doing too well, are they?
Yeah, but yeah, I mean, you can see they're giving you like sale of chicken murders and things like that. But I mean, you've used these tools. Like, they're not transformers in the tool, but like a couple of years ago, they were these models that when you use like Google Translate. So you know how well they work. Like they usually work. Now they actually work a lot better. So it's it's kind of a false comparison, but they're still not perfect by any stretch of the imagination. All right, so. So using this, like here are some ways that this works, right? So these in green, these are words that aren't part of our vocabulary. So like numbers like 2600 not part of vocabulary. Orthopedic doesn't show up enough, so it's not part of the vocabulary. Cataract was not. Here's the human translation. So here's the translation with the unknown tokens in it, and then when we now do this kind of matching replacement thing, we just we know that numbers just kind of copy down directly, especially when they're in numerical format like that, and then we just do these lookups from the dictionary. Orthopedic translates to that. Cataract translates to some word that looks like cataract. Somebody can pronounce it better. But yeah, like. And so where it might have struggled before in doing this because these were very rare words, now we have we do much better. It doesn't mean that it's oh yeah, here's another example where like a name of a company gets treated the right way. This doesn't always happen. Or this isn't perfect, as you know. We said that these aren't perfect scores. Here's an example. You can kind of see why this would happen. So here's our source phrase. Here's our human translated phrase. we have, let's see, and I'm forgetting what's going on here. Oh yeah, so was is actually so common here that it's actually not part of our translation, and what's happening is you have one of these funny things in English where we have like this, I don't even know what the term grammar is here, the correct grammatical term is, but like this was abandoning, and we're trying to get this translated into this abandon, however is the right way to say that, and this is also unknown, so it does this lookup. We have this wasn't abandoning, but it sort of lost that when it brought down the proper name into one space here, and lost this alignment of the was abandoning and just getting this was here and losing the abandoning. So this doesn't get everything right. There are still ways that this fails, and so these would be some of the reasons why that score is not perfect. So it's better. It's better than the state of the art at the time, but not perfect. Okay, so that's one way this was solved, or that is a way that this vocabulary size problem was solved to give state of the art performance. Now we're looking at the sentence length. As the length of the sentence gets longer, it becomes harder and harder to translate them properly. So this is where we see for the first time this idea of attention, or at least where it became very popular. So, sentence quality, the translation quality of any sentence degrades as it gets longer. That's just because the statistics are just more complicated, and our RNN may not have learned all those interactions very well yet. It's something similar to the rare word problem, because you're not seeing the rare word enough to do the translation properly. Here you're not seeing complex interactions of words in long sentences enough to do this translation well. And there's also some problem with just being able to propagate all that signal correctly all the way through. And one of the main problems here is something like, what we are doing here is we're representing the meaning of this whole sentence in a fixed dimensional vector. And the longer the vector is, you might expect it maybe to need more dimensions or something like that. It's kind of hard to say that's exactly the issue, but you can imagine that that's the case. And apparently in 2014 there was this kind of famous non-neural network person in this field named Ray Mooney, and he opened up his talk, kind of in criticizing the seek-to-seek models with this. This was literally the first slide in this talk. You can't cram the meaning of a whole sentence into a single vector. Although we're finding out that Ray Mooney is probably very well. But anyways, it is an issue. So how can we deal with this? Well, remember what we've been doing so far is that we have this kind of unidirectional aggregation of information as we add tokens, right? Hidden state feeds into here, produces a new hidden state, feeds in here, and so forth. And so we've got this single aggregated representation of the sentence for each layer in the network. And then we're using that as a seed to decode the rest. Well, what if, instead of that, what we could do is access the hidden states in every single one of these in such a way that it helped with the translation. And this is the idea of attention. So attention came out in this paper right here, Translation by Jointly Learning to Translate in the Line. So Benjio's on there again. Hard to get away from him when it comes to state-of-the-art papers. What you're seeing here is a plotting of the BLEU score by sentence length here. So for most neural machine translation systems at the time, the longer the sentence got, the worse the BLEU score was getting. Just because, for the reason we've just been talking about. But when they added in this attention mechanism that we're about to describe, that BLEU score, increases to something. This is not the the French to English or English to French translation problem anymore, if you're wondering about the difference in BLEU score. But it maintains itself at this level, which is really cool. So, what does this look like? What this looks like is the following. We are going to compare. We're going to compare our hidden state here in any cell that we're looking to decode. We want there to be an input. We want this to be conditioned on this history, and so far it's conditioned by a single vector that we've aggregated all the way up to this point. But now what we're going to do is allow us to basically create a linear combination of all of these states for additionally conditioning for additional input to this vector. And the way this is done is through this kind of in a kind of an interesting way. So we have two vectors, and what we do is we have some way of comparing them, some way of comparing their similarity to each other. Well, I wouldn't say similarity. Just you can have some way of comparing. It is similarity here, but some way of comparing them to each other. So we have some sort of score, and we do that for all of the hidden states in the encoder. Okay, this is obviously very simplified. And then what we do is we normalize those, right? So we add them all up and divide by that sum. So we get now this probability distribution here, or this convex combination of coefficients. And what we now do then is we take those coefficients, we multiply, each one corresponding to where it came from, and we add them all together. That's this linear combination. It's technically a convex combination of all those vectors. And we have now an additional vector that we also input into. We also provide to the cell at this stage as additional context for doing the decoding. So you still have this aggregated input here, but now you have this additional context vector. And notice that this vector that you get now additionally depends on what you've got here, right? Because we've computed these similarity scores, or these comparison scores. And we're going to learn all of this, end to end. So it's going to learn how to score these things in such a way that this context vector helps in having a more appropriate translation. This is called attention because what's happening is that this cell is now attending to these previous states, according to this attention vector, which is just the coefficients of these comparisons or these similarities. It's weird because it's all internal comparisons. It's like the same data being compared to itself, but you're learning to use these previous states in such a way that you make improvements. And yeah, these become context into your next stage in the encoder or the decoder, and you get better translations as a result of that. All right. So before I move on here, just want to stop for questions. It's almost too simple in some sense, and so it can kind of be deceiving. Oh yeah, I totally get that. But if you have questions, please ask. Again, I'll just repeat. The idea here is, I want to produce my next hidden state. The way that I do that is I take this current hidden state. I do comparisons to all my hidden states in the encoder. I use those to create coefficients that then become the coefficients of this linear combination of those previous of those encoder states, that then become part of the input to my next hidden state. And just by doing this kind of attention mechanism, I get much better translation, and in particular, I get much better translation for long sentences, because you can imagine, like, if I'm a lot further, these are really long sentences. Like, there's a lot of, there are a lot of stages here, and there's a lot of stages here. This is, at every step, this is allowing me to basically go back into all of the hidden states in the encoder and use those, like, immediately for creating the next hidden state. Transformers use this idea, and it, like, on steroids. You'll see, like, there's attention. There's a lot of these, of like a kind, this idea of, using the existing representations to update new ones. Any questions before we move on? That's really all it is. So this starts to get state of the art for other kinds of translation systems between different languages. We already had state of the art for English to French. This now gives us state of the art for English to German. And yeah, this is just like another look at these BLEU scores for the English to German. The important part here is that attention is on top there, and when we don't have attention, things are much worse as the sentences get longer. What do we pick up? What kind of ability do we pick up here? We pick up the ability to do these kinds of more difficult tasks, like double negation. So not incompatible, right? The not is a negation, the in prefix is a negation. So being able to reach back into the individual representations here at each stage of the encoder allows there to do a much better job at, for instance, doing this translation, the proper translation of doubly negative phrases. I don't know German either, so I don't know if I'm going to get this right, but that's pretty cool. Let's see, we have just a few minutes left. I want to get this last one here. So the last 10 minutes we're going to talk about language complexity. So how is language complexity dealt with? Well, it's dealt with, at least for like complex words, we deal with it with, instead of having token or like word level translations, we're going to sometimes have character level translations. So this again is dealing with something about the rareness of certain things in languages, like so the copying mechanism is one way of dealing with rare words, right? But sometimes it's not sufficient. So one way is just when you have very, very different alphabets, this becomes difficult for there to be, enough of an understanding of like how, this one actually you might be able to look up, but it's not going to be clear like how to look up all possible like proper expressions of one word and the other. And then in particular, this multi-word alignment is an interesting one, right? So like we would have maybe 2 words to say solar system, but many like languages like German, you put those together. How do we deal with those? The copy mechanism is about having tokens for each one of those things. How should we know to combine those? And in general, like there are some languages where the vocabulary is actually quite open. Like you can create like a whole bunch of words that would never exist in a dictionary, but are nevertheless like grammatically correct words. Also informal spellings, informal like uses of punctuation, things like that. We want to be able to deal with those. So one way to deal with those is to generate a character level translation when it appears that we need it. So the way this works, so English to Czech, this is a great example. Again, I don't know Czech at all, but I just know when I can see it that it looks very complex compared to English. Lots of additional, letters in the alphabet and so forth. And what you have in this case is this kind of hybrid neural machine translation system where you have a word-level translation system that's doing everything we talked about before. But when we see these unknowns, and we do this kind of alignment, what we learn to do is a character-to-character translation of those two tokens that are purportedly aligned. So, actually, this is probably not a bad example. Like jolie and cute are pretty well known. But this just as an example, the idea here is that you have another system that's just learning to do these kinds of translations of the tokens that become unknown at the character level. And so now what you're learning is that you have an additional system that's learning to how to go between these kinds of these kinds of phrases, these kinds of words at a different level, at this lower level, at the character level. And once you do that, then you get state-of-the-art translation in these systems. Sorry, I'm skipping over this. Hold on. Well, these are just saying the same thing I was just saying. The idea here is just to remind you that these are their own networks. They have their own tokens. They have their own start and end tokens, those kinds of things. And just makes the coding easier. So once you do this, now you can get state-of-the-art performance in much more difficult translation systems like English to Czech. And you can see those blue scores are not very high, but they're at least better than what you were seeing before. That's when you add the character-based. I just want to show something at the same time. So this is all based on this word level performance. This is what you would get if you're just doing character-based performance, just allowing there to be 600 characters in your RNN. And then if you hybridize it, so you have the two together, you get your new state-of-the-art in this English to Czech translation. And then, of course, you always want to have ensembles. Those always eke out a little bit more, and that's how you do it. So, there you go. So, seek-to-seek, these encoder-decoder RNNs, for a while, for a few years, were state-of-the-art, just in general for machine translation. And it wasn't, we had to go beyond just the end-to-end training and add in a few more things to deal with some of the cases where these things broke down. But when we add them all together, we're now able to translate between a bunch of different languages. However, as I said many times, and we'll now look at finally next week, most everything that we've talked about is now being replaced by a new way of dealing with sequential data, which is just the family of models called transformers. So we'll start with that next time. So good. Right, that's it for today.